Hello there, Mr. Sutton here, bringing you the BC Calculus 7-4 Part 1 Homework Solutions on Taylor series. On this problem, they want the third-order Taylor polynomial generated by cosine of x at x equals pi over 4. Since we're not centered at 0, we can't just use the Maclaurin series for this. We have to build this one from scratch. So let's find f prime, and we're going to have to go up to f triple prime to get the third-order polynomial. All of that evaluated at pi over 4. So f of pi over 4, that's just cosine of pi over 4. That's going to be root 2 over 2, just remembering our unit circle here. And then the first derivative of cosine, that's negative sine. Evaluate that at pi over 4. That's also going to be root 2, except it's negative now, so negative root 2 over 2. And then, let's see, the derivative of this, that's going to be negative cosine. Evaluated at pi over 4. That's going to be negative root 2 over 2. So it's helpful that cosine and sine both have the same value at pi over 4. And now our next derivative, our third derivative, that's going to go back to sine. And that's going to give us positive root 2 over 2. Putting it all together, we've got f of pi over 4, which is, again, root 2 over 2. Plus, now we're going to do, or actually minus root 2 over 2 times x minus pi over 4. Next, we're going to have minus root 2 over 2, and we would be dividing this by 2 factorial now, and we'd have an x minus pi over 4 squared. But because I'm dividing by 2 factorial, I'll just stick that in the denominator of this fraction. So I'll write this as negative root 2 over 2 times 2 factorial with all this other stuff. I could simplify this to 4, but I mean, why bother if I don't need to? And then finally, here we're going to have plus root 2 over 2 times 3 factorial. We're dividing by 3 factorial for that third coefficient there. And then we have x minus pi over 4 to the third power. On this problem, we have a figure with a graph of some function, and they want to know which of the following could be the second degree Taylor polynomial for our function about x equals 2. So could be is the key word. There is no way to conclusively prove that any of these actually is the second degree polynomial. It's just process of elimination on this one. So let's start by getting our basic form. Since we're going about x equals 2 instead of x equals 0, we have to have an x minus 2 when we write out our Taylor series. So I'm going to have, first off, just f of 2, whatever that comes out to. Then I'm going to have f prime of 2 times x minus 2. And finally, I'll have to have f prime, or actually f double prime of 2 times x minus 2 squared all over 2 factorial. Or just 2, I guess you could call that. So this general format with these x minus 2's means that answer choices A and B probably are not the answer. They could have done something maybe sneaky and tried to multiply things up, but they tend not to do that with a Taylor series. They just leave the center inside these squared parentheses here. All right, so we need to get a little bit more information to get rid of 2 more answer choices. So for this, we need to figure out, first off, f of 2. What should that be? Well, looking at my graph, f of 2 should at the very least be positive. That's the y value when x equals 2. So we need a positive number for f of 2. Looking at our answer choices, that doesn't help because we've got positive 2 all the way. All right, well, let's move on to f prime. What would that tell us about the function here? That would tell us the first derivative of the function at x equals 2, the slope of the function. Now we see that the original function here, f of x, is increasing at x equals 2. That means that f prime of 2 must be a positive number. We don't know what it is, but it's got to be positive. And that is enough to eliminate choice C, because in choice C, we have a negative parentheses x minus 2, meaning the f prime of 2 must have been a negative number in that one. So C is gone. Well, next we have to figure out something about f double prime, because that's going to determine whether we have a negative or positive final term here. F double prime is talking about the concavity of the original function. So the second derivative of the original function, since this function is concave up at x equals 2, that means f double prime of 2 must be a positive number as well. Well, if that's a positive number, it means we can't have negative x minus 2 squared. So that means because we can't have D, by process of elimination, it's got to be choice E. For this no calculator problem, we're given the third degree Taylor polynomial for some function about x equals 4, right here. We want to know the value of f triple prime of 4. Now, the key on this one is realizing that a polynomial generated about 4 is going to have perfect information for as many terms as they give us. So the third derivative is actually kind of embedded in this formula here. To figure out exactly what it is, let me first write out what the formula for the third derivative, or the third coefficient, I should say, ought to be. So the coefficient of x minus 4 cubed, which is where you're going to find the third derivative, that should be f triple prime of 4 over 3 factorial. Just the way these Taylor formulas are written, the derivative, the factorial, always match up. Well, what is the actual coefficient of x minus 4 to the third power? Looking up here in the polynomial they gave me, that looks to be 1 over 512. So I'm going to set this expression equal to 1 over 512. All I have to do now is actually just solve for f triple prime of 4. I can do that by multiplying both sides by 3 factorial, and that's actually just 6. So we have 6 over 512. And unfortunately, that is none of the answer choices, so we're going to have to reduce this to match. These can both reduce by, let's see here, at the very least 2. So half of 6 is 3, half of 512. You might have to do some long division, but it ends up being 256. So we have 3 over 256, which is going to give us answer choice D. For this problem, we have a function of f of x equals ln of 3 minus x, and we want to know the third degree Taylor polynomial about x equals 2. In order to construct this, we're going to need f of 2 and also the first 3 derivatives at x equals 2 for the ln of 3 minus x function. So let's start with f of 2. That's going to be just ln of 3 minus 2, or ln of 1, and that's just 0. Next, let's do the first derivative. That's going to end up being 1 over 3 minus x times a tail of negative 1, or we could call this negative 3 minus x to the negative 1 power to make it a little bit easier to take future derivatives here. And we're evaluating that at 2. So when you plug 2 in here, this is just 3 minus 2 is just 1, so this is really all just going to be 1. So really, it's just the coefficient that's going to be determining what our derivatives are coming out to. In this case, it's just going to be negative 1. Next, second derivative, we multiply negative 1 here, so that's a positive 3 minus x to the negative 2 times a tail of negative 1, so that just ends up getting negative again. So we end up with negative 3 minus x to the negative 2 evaluated at 2. This is just negative 1 again. Next derivative, we're going to have a 2 out in front. It becomes positive, but then the tail makes it negative again. So we actually have a negative 2 out in front, negative 3 power. Evaluating that at 2, we again have a 1 inside here when all this is said and done, times the negative 2 coefficient gives us negative 2 for that derivative. Okay, so let's build our polynomial now. We have f of 2, which was just 0, so we don't have to write that. Now we're going to have minus 1 times, we're going to have, this is centered at 2, so it should be x minus 2. Next, we're going to have minus 1 times x minus 2 squared over 2 factorial. Then we're going to have minus 2, parentheses, x minus 2 cubed over 3 factorial. And this does not match any of the answer choices. None of the answer choices have factorials. So we're going to modify things a little bit. This 2 factorial, well, that's really just a 2. So that doesn't really require a whole lot. Over here, we've got 2 over 6, which we can reduce to 1 over 3. And that is going to match answer choice. Let's see, we want the one with 3 negatives. So that's going to end up being choice B. On this problem, we have a twice differentiable positive function, and they're telling us f of 1 is 15, f double prime of 1 is 20. That might be important. Values of f prime are given in this table. First task is to write an equation for the line tangent to our original function at x equals 1, and then turn around and use this to approximate f of 1.4. So I'm going to start with my general tangent line formula. L of x equals f of a plus f prime of a times x minus a. And now that you've done a little bit with Taylor series, you might recognize that this is really just a linear polynomial using our Taylor formula. So we've got f of 1 in this case plus f prime of 1 times x minus 1. And now we have to fill in some values. F of 1, they actually told us that in the stem here. They said that was 15. F prime of 1, we can look up in the table. That's going to be 8. And then we have x minus 1 still. So this is the equation of the tangent line. You actually have solved this part of the problem when you write this out. Next thing we need to do is approximate 1.4 with this. So we're just going to plug in 1.4 for x, and we're going to write f of 1.4 is approximately equal to all of this. And you could actually stop there because it's all constants, but if you wanted to simplify, this is, let's see, 8 times 0.4, which is going to be 3.2. Add that to 15 and we have 18.2. On this part of the problem, they want us to use MRAM with two subintervals to figure out 1 to 1.4 integral of f prime of x, and then use that approximation to figure out the value of f of 1.4. All right, so one step at a time, let's approximate the integral from 1 to 1.4 of f prime. I'm going to say that that is approximately equal to the following. So if I'm using midpoint RAM with two subintervals, that means I have a rectangle going from 1 to 1.2 and another going from 1.2 to 1.4. So the base of the first rectangle is just 0.2, the distance between these. And since I'm using MRAM, I have to use the midpoint y value, which is going to be 10. So 0.2 times 10. My next rectangle, I still have a base of 0.2, but now I'm using that middle value of 13. And I could leave it like this, but if I wanted to simplify, 10 plus 13 would be 23. And if I factor the 0.2 out of there and multiply it by the 23 that I get, that would be, let's see here, 2 times 23 would be 46. Move the decimal, that's 4.6. Now they wanted us to use this approximation to estimate f of 1.4. So if I already have a value of f of 1, and they again said that that was 15, and I have the value of the integral of the derivative of f from 1 to 1.4, then to find f of 1.4, I can just use my fundamental theorem. So this is just going to be f of 1 plus integral from 1 to 4 of f prime. And now that means I've got 15 plus 4.6. And I wrote exactly equals for this first part because f of 1.4 is exactly f of 1 plus the true integral. But since we estimated the integral value, it's now approximately equals 15 and 4.6, or 19.6. On this part of the problem, we are again approximating f of 1.4. This time around, though, we're using Euler's method, starting at 1 with two step sizes of equal size. All right, well, we're going to have to do this in two steps. Step 1 is going to be to approximate f of 1.2, and then we'll use that approximation to figure out f of 1.4. So let's see here. That means for f of 1.2, we need f of 1 plus f prime of 1 times the step size of, it'll be 0.2 to go 0.4 in two steps. F of 1 we have from the problem gave it to us, it's 15. F prime of 1 we can look up in the table, that's just 8. So we have 8 times 0.2. This is 1.6 over here. 15 plus that is going to be 16.6. And now we're going to move on and use this value to actually approximate f of 1.4. So that value is going to be f of 1.2, or at least our approximation of it that we just got, plus f prime of 1.2 times our step size of 0.2. F of 1.2, again, that's approximately 16.6. F prime of 1.2, that's something we can look up in the table here. That's actually 12, and we still have that step size of 0.2. So this is going to be, let's see here, this would be 2.4 if we multiply this out. So this is going to be 19 if we add all that together. So there's our approximation using Euler's method. So for this last part of the problem, we've already approximated f of 1.4 with Euler's. We've used the fundamental theorem with MRAM, and we've also used a tangent line approximation. Now we're going to use a second-degree Taylor polynomial to do this one more time. So to write that out, I need f of 1, which is going to be, they gave us that was 15, but let me just write out the general formula. So we're going to have f of 1 plus, this is going to be f prime of 1 times x minus 1, since we're centering this around x equals 1. And then we're going to have f double prime of 1 times x minus 1 squared all over 2 factorial. Let me actually fill in some values now. F of 1 we said was 15. F prime of 1 we can get in the table, that's 8. So we have 8 times x minus 1. f double prime of 1, they gave us that value flat out here. That's 20. So we have 20 x minus 1 squared over 2. And all I have to do now is just plug in 1.4. So I can say f of 1.4 is approximately equal to p sub 2 of 1.4, which is all this stuff with 1.4 plugged into it. Now I can actually leave this because it's all constants and that counts as a correct final answer. If I wanted to really get fancy, I could try simplifying this. So we've got 15, and this is 8 times 0.4, so that's 3.2. And this last mess over here, well, let me think here. This is going to be 0.4 squared, so that's going to be 0.16. 20 over 2 is 10, so we have 10 times 0.16, which is 1.6. Adding all this together, this is 15 plus 4.8, or 19.8, which is at least pretty close to what we got with the other approximations.